Welcome to Listen and Learn Code, the podcast where you learn about programming and tech topics without needing to watch a screen. I'm Michael, your host. In this series, we'll dive deep into solid principles specifically tailored for Python developers. This podcast is designed to help you grasp both the foundational and advanced aspects of solid principles, making it accessible wherever you are. Today, we'll start with our first chapter on solid principles, focusing on their importance in Python development. Our course objectives are clear. By the end of this lesson, you'll have a solid understanding of each solid principle and its relevance to Python development. You'll also be able to identify and correct design issues in your Python code using these principles. The ultimate goal is to empower you to apply these principles to write clean, maintainable, and scalable Python code. Now let's start with the first chapter, an introduction to solid principles. So, what are solid principles? These principles are a set of 5 fundamental design guidelines that help developers create better software. They were introduced by Robert C. Martin, commonly known as Uncle Bob, and they aim to make software more understandable, flexible, and maintainable. The word SOLID is an acronym where each letter stands for specific principle, single responsibility, open/closed, list of substitution, interface segregation, and dependency inversion. Together, these principles form a robust foundation for object-oriented programming. Now, why are these principles important in Python development? Python is known for its simplicity and readability, but as projects grow in complexity, maintaining clean and efficient code becomes challenging. This is where solid principles come in. They provide a framework that helps manage complexity by guiding the structure of your code. By following these principles, you can reduce the chances of bugs, make your code easier to understand, and facilitate future changes or extensions without breaking existing functionality. Let's talk about how solid principles align with Python's design philosophy. Python's design emphasizes readability and simplicity. Solid principles complement this by encouraging developers to write code that is modular and easy to understand. For instance, Python encourages the use of clear and concise functions, and the single responsibility principle emphasizes that each function or class should have only one responsibility. This alignment makes it natural to apply solid principles in Python projects. Let me give you a brief overview of each principle. First, we have the single responsibility principle. This principle states that every class or function should have only one reason to change, meaning it should have one responsibility or job. The idea is to make your code more modular and easier to maintain. Next, there's the open/closed principle. This principle suggests that your code should be open for extension, but closed for modification. In simple terms, you should be able to add new features to your software without altering existing code, thus avoiding unintended side effects. The third principle is the list of substitution principle. It means that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. In Python, this often translates into ensuring that derived classes or subclasses don't alter the behavior that clients expect from the base class. The fourth principle is the interface segregation principle. It advises that no client should be forced to depend on methods it does not use. This is about creating small, specific interfaces rather than large, general-purpose ones. In Python, this principle encourages you to keep your classes and methods focused on a particular task. Lastly, there's the dependency inversion principle. This principle states that high-level modules should not depend on low-level modules. Instead, both should depend on abstractions. In Python, this often involves using dependency injection or inversion of control techniques to make your code more modular and flexible. In summary, solid principles are crucial for building robust, flexible, and maintainable Python applications. They align well with Python's philosophy of simplicity and readability, making them an essential part of any Python developer's toolkit. As we move forward in this lesson, we'll dive deeper into each of these principles, providing examples and practical advice to help you apply them in your Python projects. Let's start with understanding what the single responsibility principle is. The single responsibility principle states that a class or function should have only one reason to change, meaning it should only have one responsibility or job. In simple terms, each piece of your code should focus on doing just one thing and doing it well. This principle is important because it makes your code easier to understand, easier to test, and easier to maintain. When a class or function has only one responsibility, it's less likely to be affected by changes in other parts of your code base. This makes your code more stable and reduces the risk of introducing bugs when you need to make changes. Now that we understand the definition of the single responsibility principle, let's explore why it is so important in Python development. The key benefit of following this principle is that it helps keep your codebase clean and understandable. When a class or function is responsible for only one task, it becomes much easier to comprehend what that piece of code is supposed to do. This clarity is crucial, especially when working on large projects or in teams, as it makes the code easier to navigate and work with. even for someone who didn't originally write it. Furthermore, having single responsibility classes or functions also makes your code easier to test. When each piece of code has only one job, you can write more focused and precise tests, which leads to better test coverage and more reliable code. This is because there's less risk of one part of the code affecting another in unexpected ways. Let's move on to Python-specific examples where the single responsibility principle is often violated. A common violation occurs when a class or function tries to do too many things at once. For example, imagine you have a class that handles both the data storage and the data processing for a particular feature. This would violate the single responsibility principle because the class now has two responsibilities, managing data and processing data. This kind of design can lead to problems as the code grows, making it difficult to maintain and extend. Another example might be a function that not only retrieves data from a database but also formats and displays it. Here, the function is taking on multiple responsibilities, which can lead to messy, difficult to maintain code. To correct these violations and adhere to the single responsibility principle, we need to refactor the code. Refactoring involves restructuring existing code without changing its external behavior to improve its internal structure. In the case of a class that handles both data storage and processing, you would split these responsibilities into separate classes. One class could be responsible for managing data storage, while another class could handle data processing. This way, each class has only one job, making the code easier to maintain and extend. For a function that both retrieves and formats data, you would separate the data retrieval into one function and the formatting into another. This separation ensures that each function has a single responsibility, aligning with the principle. Now let's discuss practical advice on how to ensure that your classes and functions in Python adhere to the single responsibility principle. First, always ask yourself what the main responsibility of a class or function is. If you find that it has more than one responsibility, it's a sign that you might need to split it into multiple parts. Keep an eye out for classes or functions that have words like and in their names, as this can be an indicator that they are trying to do too much. It's also helpful to think about potential reasons why you might need to change the code in the future. If you identify multiple reasons for change, then the code likely has multiple responsibilities and should be refactored. In practice, adhering to the single responsibility principle requires continuous attention and discipline. As you develop your code, regularly review your classes and functions to ensure they are focused on just one task. This might mean periodically refactoring your code as new features are added or as the codebase evolves. By consistently applying this principle, you'll create a codebase that is not only easier to understand, but also more adaptable to change, making future development smoother and less error-prone. This careful attention to single responsibility will pay off in the long run, helping you build robust Python applications that can grow and change with ease. Let's continue by exploring the next principle in the solid framework, the open/close principle. This principle is essential for building flexible and maintainable software, and understanding it will greatly enhance how you approach Python development. The open/close principle states that software entities like classes, modules, and functions should be open for extension but closed for modification. What this means is that you should be able to add new functionality to your software without altering the existing code. The significance of this principle lies in its ability to provide stability and flexibility at the same time. When your code is open for extension, it means you can introduce new features or behaviors without modifying the existing system. This is crucial because every time you modify existing code, you run the risk of introducing bugs or breaking something that already works. On the other hand, by keeping the code closed for modification, you protect the integrity of the existing codebase, ensuring that what already works continues to work. Finding the right balance between flexibility and stability in Python code is key when applying the open/close principle. Flexibility allows your code to evolve and adapt to new requirements, while stability ensures that the existing functionality remains reliable. Python's dynamic nature provides tools that can help achieve this balance, but it also means that developers need to be mindful of not introducing unnecessary complexity when making the code extendable. To implement the open/close principle in Python, two common techniques are often used: inheritance and composition. Inheritance allows you to create a new class based on an existing one, where you can extend or override certain behaviors without changing the original class. For instance, if you have a base class that handles basic file operations, you can create a subclass that adds encryption features to those operations without altering the original file handling code. This adheres to the open/close principle because you've extended functionality without modifying the existing class. However, it's important to use inheritance wisely. If used incorrectly, it can lead to tightly coupled code that is difficult to maintain. Composition, on the other hand, is often preferred over inheritance because it promotes a more flexible and decoupled design. With composition, instead of extending a class, you build new functionality by combining objects that encapsulate different behaviors. For example, if you have separate classes for handling reading and writing to files, you can create a new class that uses instances of these classes to add logging or monitoring features, all without altering the original classes. This approach keeps the codebase stable and allows for new features to be added easily, adhering to the open/close principle. Let's look at a real-world example where the open/close principle improves code design in Python. Imagine you're developing a payment system that initially supports only credit card payments. Over time, you need to add support for other payment methods, like PayPal or cryptocurrency. If you had designed the payment system to be open for extension but closed for modification, adding these new payment methods would be straightforward. You would introduce new classes for each payment method, following the existing payment interface without changing the core logic of the payment system. This design ensures that the system remains stable while being flexible enough to accommodate future payment methods. Now, let's discuss practical strategies for designing Python classes that are open for extension but closed for modification. One effective strategy is to define clear and stable interfaces or abstract base classes that outline the expected behavior. By coding to these interfaces, you can ensure that new features can be added without altering the core functionality. Another strategy is to use design patterns that inherently support the open/close principle. For instance, the strategy pattern allows you to define a family of algorithms or behaviors and make them interchangeable without modifying the code that uses them. A template method pattern is another example where you can define the skeleton of an algorithm in a base class, but allow subclasses to override specific steps of the algorithm, providing extension points without changing the overall structure. In summary, the open/close principle encourages you to design your Python code in a way that makes it easy to extend with new features, while keeping the existing codebase stable and unchanged. By using techniques like inheritance and composition, and by following design patterns that support this principle, you can create software that is both flexible and robust, capable of evolving over time without the need for risky modifications. This approach not only reduces the likelihood of introducing bugs, but also makes your code easier to maintain and scale as your project grows. Continuing from where we left off, let's now explore the third principle in the solid framework, the Liskov substitution principle. This principle is closely related to inheritance and polymorphism in object-oriented programming, and understanding it is crucial for designing systems that are both flexible and reliable. The Liskov substitution principle is named after Barbara Liskov, who introduced the concept in the late 1980s. The principle states that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. In simple terms, if you have a class hierarchy, you should be able to use an instance of a subclass wherever a superclass object is expected, and the program should behave correctly without any errors or unexpected behavior. The Liskov substitution principle plays a vital role in inheritance and polymorphism. Inheritance allows you to create a new class based on an existing one, inheriting its properties and behaviors. Polymorphism enables you to treat objects of different classes through the same interface, typically the interface of a superclass. When you follow the Liskov substitution principle, you ensure that these inherited and polymorphic relationships are safe and predictable. This means that a subclass should only extend the behavior of its superclass without altering its intended functionality. To better understand this, let's talk about some common violations of the Liskov substitution principle in Python and how to address them. A typical violation occurs when a subclass overrides a method from the superclass in a way that changes its expected behavior. For instance, if a method in the superclass is supposed to return a positive integer, but the subclass implementation returns a negative integer or raises an exception instead, this would violate the Liskov substitution principle. Such a situation can lead to unexpected issues in the program, especially if other parts of the code rely on the expected behavior of the superclass. To fix violations of the Liskov substitution principle, you need to ensure that the subclass adheres to the same contract as the superclass. This means that if a method in the superclass has a certain precondition or postcondition, the subclass should not weaken these conditions. In other words, the subclass should meet or exceed the expectations set by the superclass. If the subclass introduces behavior that significantly differs from the superclass, it might be a sign that the subclass should not inherit from that particular superclass in the first place. Instead, you could consider designing a new class or interface that better fits the intended behavior. Let's look at how to refactor class hierarchies in Python to comply with the Liskov substitution principle. One approach is to use interfaces or abstract base classes to define clear and consistent behavior that all subclasses must follow. By doing this, you make sure that any subclass is required to implement methods that adhere to the same rules as the superclass. Another approach is to avoid deep inheritance hierarchies altogether. Sometimes composition is a better choice than inheritance. By composing objects rather than relying heavily on inheritance, you can build more flexible systems where the behavior of individual components is clearer and easier to manage. Now let's discuss some practical advice for ensuring that subclasses in Python can replace their base classes without altering the correctness of the program. First, always test your subclasses in the context where the superclass is expected to be used. This will help you catch any deviations in behavior early. Make sure that the methods in your subclasses do not introduce unexpected side effects or change the way data is handled. Another key practice is to follow the principle of least surprise. This means that your subclass should behave in ways that are predictable based on the superclass. If the superclass method returns data in a specific format, ensure that the subclass method does the same. Additionally, when designing subclasses, think about the long-term implications of overriding methods. Ask yourself whether the changes you are making are truly necessary and whether they could lead to confusion or errors down the line. If the subclass needs to behave very differently from the superclass, it might be a sign that the inheritance hierarchy needs to be reconsidered. In conclusion, the Liskov substitution principle is all about maintaining the integrity of your class hierarchies in Python. By ensuring that subclasses can be used in place of the superclasses without altering the program's correctness, you create more reliable and maintainable code. This principle helps you avoid subtle bugs that can arise from unexpected changes in behavior and ensures that your code remains flexible and scalable as it evolves. Following this principle, along with the others in the solid framework, will lead to better designed Python applications that are easier to maintain and extend over time. Continuing from where we left off, let's now delve into the fourth principle in the solid framework, the interface segregation principle. This principle focuses on how we design interfaces in our code, and it plays a crucial role in creating systems that are easy to understand and maintain. The interface segregation principle states that no client should be forced to depend on methods it does not use. Essentially, this principle encourages the creation of small, specific interfaces rather than large, general-purpose ones. The importance of this principle lies in its ability to reduce the complexity and improve the clarity of your code. When a class is forced to implement a large interface that includes methods it doesn't need, the class becomes bloated and harder to understand. It also makes the code more difficult to maintain because any changes to the interface can affect many classes that might not even be using the parts that were changed. In Python, which is known for its simplicity and readability, the interface segregation principle is particularly valuable. Python's dynamic nature allows us to define interfaces and abstract classes that are lightweight and focused. Instead of having one large interface that tries to cover all possible functionalities, we can create multiple smaller interfaces, each tailored to a specific aspect of the functionality. This approach makes our code more modular, meaning that each part of the code does one thing, and does it well, without unnecessary complexity. To apply the interface segregation principle in Python, you should focus on designing interfaces and abstract classes that are narrow in scope. This means that each interface or abstract class should define a small set of related methods that serve a specific purpose. For example, if you have a system that handles different types of notifications, you might have separate interfaces for sending emails, sending text messages, and logging notifications, rather than one large interface that includes methods for all these activities. By breaking down the interfaces in this way, each class that implements an interface only needs to worry about the methods that are relevant to its specific role. Now, let's discuss how to refactor large interfaces into smaller, more specific ones. Suppose you start with an interface that has methods for several unrelated tasks. As you analyze the interface, you might notice that different classes only need certain methods from the interface. In this case, you would break the large interface into multiple smaller interfaces, each representing a coherent set of responsibilities. This refactoring process helps you align your code more closely with the interface segregation principle, making your code base more maintainable and easier to understand. Another important aspect of applying the interface segregation principle in Python is avoiding situations where classes are forced to depend on methods they do not use. This can happen when you design an interface that is too broad, requiring classes to implement methods that are irrelevant to their specific tasks. To avoid this, always aim to design interfaces that are as specific as possible. If a class only needs to interact with a small part of an interface, that's a sign that the interface might be too large and should be split into smaller, more focused interfaces. Practical advice for adhering to the interface segregation principle in Python includes regularly reviewing your interfaces to ensure they are not becoming too broad. As your project evolves, the needs of different classes may change, so it's important to keep interfaces aligned with those needs. Additionally, be mindful of the relationships between your classes and interfaces. If you find that many classes are implementing an interface but only using a fraction of its methods, consider refactoring the interface into smaller ones that are more aligned with the specific tasks of those classes. In summary, the interface segregation principle is all about designing your Python code in a way that keeps interfaces small, specific, and focused on the needs of the classes that use them. By doing so, you reduce the complexity of your code, making it easier to understand, maintain, and extend. This principle helps you create a codebase where each part of the system is only responsible for what it really needs to do, leading to cleaner, more modular code that can evolve more gracefully over time. Continuing our discussion on the solid principles, let's now explore the final principle, the dependency inversion principle. This principle is crucial for designing software that is both flexible and easy to maintain, particularly as your projects grow in size and complexity. The dependency inversion principle states that high-level modules should not depend on low-level modules. Instead, both high-level and low-level modules should depend on abstractions. To understand this better, let's break it down. Higher-level modules are usually the parts of your code that deal with core business logic or the main functionality of your application. Low-level modules, on the other hand, are the parts that deal with the details, such as working with databases, file systems, or external APIs. The dependency inversion principle suggests that the higher-level logic of your application should not be directly tied to these low-level details. Instead, both should depend on abstract interfaces or classes that define how they should interact. The importance of this principle lies in its ability to make your code more modular and easier to change. When high-level modules depend directly on low-level modules, any change in a low-level code, such as switching to a different database or modifying how files are read, can force you to make changes throughout your entire application. This creates a tightly coupled system that is difficult to maintain and extend. By adhering to the dependency inversion principle, you create a system where the high-level modules are insulated from changes in the low-level modules, making your codebase more resilient to change. In Python, you can implement the dependency inversion principle using techniques like dependency injection and inversion of control. Dependency injection is a design pattern where objects or functions receive their dependencies from an external source rather than creating them directly. For example, instead of a class directly instantiating a database connection, you would pass the database connection to the class from outside. This allows you to easily replace the database connection with a different one, such as for testing or switching databases, without altering the class itself. Inversion of control is a broader concept where the flow of control in a program is inverted compared to traditional procedural programming. Instead of the high-level modules controlling everything, they delegate control to the abstract interfaces, which can then interact with different implementations of the low-level modules. This approach reduces the direct dependencies between high-level and low-level modules, making the system more modular and easier to manage. Let's look at some practical examples of applying the dependency inversion principle in Python projects. Imagine you're building an application that needs to send notifications through different channels, like email, text messages, and push notifications. If the high-level module directly interacts with specific classes for each type of notification, the system becomes tightly coupled. Any change in how one type of notification works could affect the entire system. Instead, you could define an abstract interface, such as notifier, with methods like send. Each type of notification, email, text message, push notification would then implement this interface. The higher-level module would depend only on the notifier interface, not on the specific implementation. This way, you can add new types of notifications or change existing ones without modifying the high-level module, making your system more flexible and easier to maintain. Now, let's discuss some strategies for designing Python applications that are modular and easy to maintain, in line with the dependency inversion principle. One effective strategy is to always start by defining the interfaces or abstract base classes before implementing the actual logic. This helps you focus on what the module should do rather than how it should do it, which encourages decoupling from the start. Another strategy is to use Python's dynamic features, like duck typing, to further reduce dependencies. In duck typing, an object's suitability is determined by the presence of certain methods and properties, rather than the object's actual type. This allows different objects to be used interchangeably as long as they provide the required behavior, which aligns well with the dependency inversion principle. You should also regularly review your code to identify places where high-level modules are directly dependent on low-level details. If you find such dependencies, consider refactoring the code to introduce abstractions. For example, if a high-level module is creating instances of a low-level class, consider passing the instances as arguments instead, allowing the class to depend on an abstraction rather than the concrete implementation. Finally, when writing tests, the dependency inversion principle makes it easier to mock or stub dependencies. Because high-level modules depend on abstractions rather than concrete classes, you can easily replace the real implementations with mock objects in your tests. This leads to more effective unit testing, as you can isolate the module under tests from the rest of the system. In conclusion, the dependency inversion principle helps you design Python applications that are more modular, flexible, and easier to maintain. By ensuring that high-level modules depend on abstractions rather than concrete implementations, you can build systems that are more resilient to change and simpler to test and extend. This principle, along with the others in the solid framework, will guide you toward writing cleaner, more maintainable Python code that can adapt and grow over time. As we conclude this lesson on solid principles, let's take a moment to recap the key takeaways and reflect on the importance of these principles in Python development. We began our journey by exploring the single responsibility principle, which teaches us that every class or function in our code should have only one reason to change. This principle helps keep our code clean, focused, and easy to understand. By ensuring that each part of our code has a single responsibility, we reduce the complexity and make our code more maintainable in the long run. Next, we discuss the open/close principle, which guides us to design our classes in a way that they are open for extension but closed for modification. This principle is crucial for building systems that are flexible and resilient to change. By adhering to this principle, we can add new functionality to our code without risking the stability of what already works, making it easier to adapt and grow our projects over time. We then moved on to the Liskov substitution principle, which reminds us that subclasses should be able to replace their base classes without altering the correctness of the program. This principle ensures that our inheritance hierarchies are well structured and that our subclasses truly extend the behavior of their superclasses without introducing unexpected side effects. By following this principle, we create more reliable and predictable code. After that, we delved into the interface segregation principle, which emphasizes the importance of designing small, specific interfaces rather than large, general-purpose ones. This principle helps us avoid forcing our classes to depend on methods they do not use, leading to cleaner, more modular code. By keeping our interfaces focused, we make our code easier to understand and maintain, as well as more adaptable to future changes. Finally, we explored the dependency inversion principle, which teaches us that higher-level modules should not depend on low-level modules, but both should depend on abstractions. This principle is key to creating systems that are decoupled, modular, and easy to maintain. By designing our code in this way, we make it more flexible and easier to extend or modify without disrupting the entire system. In summary, the solid principles provide a powerful framework for designing software that is clean, maintainable, and scalable. They guide us to write code that is easy to understand, test, and extend, helping us build systems that can evolve gracefully over time. Whether you're working on a small project or a large-scale application, these principles are essential tools for ensuring the long-term success and stability of your software. As you continue to develop your skills in Python and software design, keep these principles in mind. Practice applying them in your projects, and take the time to reflect on how they influence the quality of your code. The more you incorporate these principles into your daily coding habits, the more natural they will become, leading to better, more reliable software. Thank you for joining me on this deep dive into solid principles. I hope this lesson has provided you with valuable insights and practical knowledge that you can apply in your Python development journey. Remember, mastering these principles takes time and practice, so be patient with yourself as you continue to learn and grow as a developer.